Hello, everyone. This is Qin from the Climate Dynamics Prediction Laboratory in Purdue University. This video will serve as a pre-recorded version of a cyber training workshop held by Purdue University that is going to take place on June 1st and 2nd of 2021. Taking heat stress extreme prediction from the CNIF6 archive as an application case, we will cover 3 practical modules, including climate data access, processing, and visualization. We will also have an extra video talking about how to use Cython to speed up your Python code. So in total, we will have 4 videos, one for each of them. And this is the third one for climate data visualization. Now let's go into the Jupyter Notebook. In this tutorial, we will first introduce the plotting functionality of X-ray, which can enable you to make a plot very quickly. And then we will talk about how to use Cartopy to make publication quality maps. First, let's import some packages. This CMaps package will make us able to access the NCL color maps. We will use this North American air temperature dataset in the tutorial of X-ray as an example to show the plot functionality of X-ray. Let's first read that. We got an X-ray dataset. And let's first try to make a one-dimensional plot. And you can see that here I choose the 10th latitude and 10th longitude. So in this way, we will get a one-dimensional time series. And because the time series has a length of nearly 3000, it may be too long to plot over here. So I only choose the first 200 time steps and make a plot. We can pass in a series of arguments over here. For example, I ask the color to be purple, and I set the type of marker and also figure size. And we can see that because of the labeling system of X-ray, the plot function can extract its information to make very informative plots. For example, we can know that our latitude is 50 degrees and longitude is 225 degrees. And also we have the time as x-axis, the labeling system, and also the Y label is all very useful information. Well, now let's try to make a plot that contains 2 superplots. Well, first we use this PLT superplot function to create a plot with 2 superplots. They contain 2 columns, and we also set the figure size. And then we make a line plot to the first axis and make a histogram plot to the second axis. You can see we have a plot with 2 superplots, with a line plot on the left, histogram plot on the right. And we also have lots of useful information here extracted from the labeling system of X-ray. Well, sometimes we want to compare the variation of multiple time series, and X-ray can make this very easy. For example, over here, I choose 1 longitude and 3 latitudes. So in this way, I will get 3 time series. Then I make a line plot. And since in this case, we actually have 2-dimensional data, so I need to explicitly tell them that the time axis is the x-axis, and we also set the figure size. So over here, you can see we have 3 lines correspond to the 3 time series, and we have the information of latitudes. So you can see the low latitudes have a relatively higher temperature, and it all makes sense. Well, X-ray can also make it very easy to plot a 2-dimensional map. In this case, we select a particular time step, which is a 2-dimensional array with latitude and longitude dimension. And we just call plot. It will plot a 2-dimensional map over here. And again, we have lots of useful information. We can see that the time step we choose is 2013, May 6th. And also we have this longitude, latitude label, and the color bar scale label. It's all very useful. And similarly, for 2-dimensional data, we can make a contour plot or a field contour plot. We can pass in a series of arguments over here. For example, I ask the color map to be blue, white, red over here. And here I further change the unit from Kelvin to Celsius degree, and then plot the field contour plot, and still ask the CMap to be blue, white, red. Here I also ask the levels to be this range, and this will help me to set the range of color bar scale from -30 to 30 with a step of 5 degrees. And if you are not satisfied with this label that X-ray automatically created for you, you can always set it by yourself using this PLT, Y label or X label. You can also set a title of this plot. Another very useful functionality that provided by X-ray's plotting function is faceting. It will help us to panel several superplots together very quickly. For example, over here, in this plot, we have 4 superplots correspond to the average temperature of each season. They share the same color bar here. We achieve this by first, we change the unit from Kelvin to Celsius degrees, and we group by season, and we calculate the mean value within each season, and then we call the plot function. Since in this case, we will have a 3-dimensional array with latitudes, longitudes, and a season. So we need to tell the plotting function that longitude is the x-axis and latitude is the y-axis, and the column to be season. And we ask the plotting function to wrap for each 2 columns. In this way, we can view the average temperature of 4 seasons simultaneously and compare them. It's all very convenient. X-ray also support other types of plot like stream plot, quiver, and scatter, and you can find the information over this link. X-array's plot functionality is very useful for us to make a quick and dirty plot. And now we will learn how to use Cartopy to make publication quality maps. To start things off, we will first introduce some basics of Cartopy to give you some ideas about what Cartopy can do. We will first create a basic map projection without using any real data. We will use the Cartopy feature interface to add some geographic features like ocean, lake, coastlines, and country borders. We will also add longitude and latitude grid lines. Now let's look at the code line by line. First, we create a figure and define the figure size. And then we create an axis with a basic plate carré projection. And you can always try the different projection like Robinson. And then this link contains a full list of Cartopy map projections. And then we want to add some nature features to this map using the Cartopy feature interface, the C feature. We do it by this X add features, the C feature land. And we also ask the edge color to be orange and the face color to be green, and also Z order to be 0. This Z order is very useful if you want to overlay multiple features with each other. And a lower Z order will be drawn first, which means it will be at the bottom level. So by setting the Z order to be 0, we make sure that the lake feature will be drawn on top of land feature. And this is what we want. Then we add the ocean feature, and let's see what we get. Yeah, this is what we expected. And the next step, we want to try a different projection style. Let's say we want to try Robinson projection. We have a Robinson projection style. And well, now we want to add some country borders on top of that. Let's first return to this normal plate carré projection. And we uncomment this country border code. We do this by X add feature, this C feature, nature earth feature. The category is culture, and with the name of admin 0 countries, we set a scale to be 50 million. It's not 50 meters. And we have 3 options over here, the 10 million, 50 million, and 110 million. And we set the face color to be none, which means we don't want to fill in color within the country. But we want the edge color to be black, and also the line width to be 0.2. Let's see what we get. Now we have the country borders on top of this map. Next step, we want to draw some longitude and latitude grid lines and also draw the grid line labels. First, let's still uncomment the code. We can see we do this by X grid lines and passing the projection that we use, and also line width, and we want the color to be gray. We want to draw the grid labels. the line style we want to be dash. And we use this mticker fixed locator to control where we want to draw the latitude and longitude grid line labels. And further, we turn off the grid line label on the top and right side by this. This means that we only want the grid line labels on the bottom and the left side. Now let's plot the map. Yes, that's what we expect. We have these grid lines and we have the grid line labels at the place we want. And next step, we want to make a map with real data. First, we're reading our result from data processing module, which is the X-ray data set, and it contains two data variables. The mean DF and the Q95DF correspond to the changes of weather temperature from the first year to the last year of this century at both the annual mean level and the 95th percentile level. And then we mix we can see the code. Yeah, I already make the plot here, and we see the code line by line. We still first create a figure and define the figure size, and we generate an axis with this projection. And then we draw the coastlines with a scale of 50 million. And next, we set the color bar scale levels to be vary from -10 to 10 with a step of 2 degrees. And then we call the plot function. Here we only plot the difference of annual mean level weather temperature. And we draw this plot to the axis that we just created. And we set the transform as predicatory. So what's transform and what's the difference between the projection? Well, the projection over here is actually telling Python and Cartopy that how we want our map look like. Do we want to look like a predicatory projection, or we want to look like a Robinson projection? And this transform is actually telling Cartopy about the actual coordinate system of our data. In this case, our data has a regular latitude and longitude coordinate system. So we set the transform as a normal predicatory coordinate system, and we shouldn't change that. Next, we set the color map. This is a color map from the NCL, and we can have access to that by using this CMaps Python package. And we set the color bar scale levels. Here, the add color bar equals false will let X-ray do not plot color bar automatically, which they will do by default, because we want to control the look of color bar by ourselves. Here we draw the color bar, and the first argument temp is returned by this plot function. It means that this color bar is for this plot. And we set the orientation of the color bar to be horizontal. This shrink control the size of color bar relative to the axis. And this pad control the distance between color bar and the map. This aspect control the width and height ratio of color bar. And the ticks control where we should put the ticks and labels on the color bar. And we can also control the label size of the color bar. And finally, we add a title. And let's look at that. Yes, it looks good. And you can always play with the parameters over there to say how it's going to affect your map. For example, we can change the aspect ratio from 20 to 30. And let's see, it will make the color bar thinner. Well, in this case, we make a global map containing both the land and the ocean. But sometimes, maybe we only want to plot data over the land because that's where we live, or we only want to make a plot over a certain country. And in this case, region mask is a very handy package to mask land and countries or certain regions. And in addition, a combination of X-ray and region mask will make it very easy to do statistics over a certain region. For example, if we want to calculate the national average temperature over China, region mask will be very helpful for this. First, we import the region mask, and we want to first use this land mask to plot our data over land only. And we can create a land mask by calling this function. This diff is our X-ray data set, and the region mask will treat it as a template to create a land mask based on the latitude and the longitude of this X-ray data set. And what we get is another X-ray data array it shares the same coordinate Cython with this div. And we can see that over the land regions, it has a value of 0, and over the ocean, it has an AA. Now let's see how to use this land mask to make our plot. And compared with the previous code that we used to generate this map, the only change happens over here. We add a where land mask equals 0. This will create a new X-ray data array that only keep the value of the land, and the value of the ocean will be turned to NAA. And then we make the plot. Let's see what we get. That's what we expect. We only have values of the land area. Next, let's see how to use country mask to plot a map over a particular country. Well, within region mask, each country has a code, and we can view it as a plot by calling this function. We can also create a country mask like what we have done for the land mask. We use this function and also pass in div as a template. This country mask is another X-ray data array filled with country code, and over the oceans, the value will still be NAA. Now let's use this country mask to plot a map over a particular country. Let's say we want to plot only over the United States. It has a country code of 4. Again, the only change happens over here. We ask the country mask to equals 4, and this will only keep the values over the United States. And let's make the plot. Yes, we only have values over the United States. And since there is no value in other region of the world, we may want to zoom in the area of the US, and we can do it by X, set extent. And this is a range of longitude and a range of latitude. And we also want to add a feature of country borders. Or in this way, we only show the area of United States. It doesn't look good, but you got the idea. Finally, we have an example of using region mask to do statistics on a certain region. For example, we want to calculate land average temperature. Here we are passing is where land mask equals 0, and we're weighted by the coast and latitudes. And then we calculate the mean value over both lat and long dimension. And what we get is the land average temperature. Next, we want to introduce how to plot multiple maps sharing the same color bar. First, we define a function called superplot to make each individual plot, and we pass in 4 arguments: the data, which is the actual value that we plot, the axis, the color map, and also the norm. And we will introduce this norm later. And then we'll define another function called plot, which actually makes the whole figure. And within this function, we first define the figure and the figure size. We add 2 superplots, and here the 1-to-1 means that we want 2 superplots, 1 row, 2 columns, and this is the first column. And similarly, this is the second column, and we also set the projection. And this function returns the axis object. We call it axis 0 and x1. This superplot adjust is very useful to adjust the relative position of different superplots. This bottom, left, right, and top define the position of each individual plot. And this H space, W space, define the distance between different superplots over both the height dimension and the widest dimension. And this 3 lines of code is trying to add annotation to each superplot. Here we define the position of annotation, and this is the content of the annotation, and also the font size. And we define the color map, the levels, and here comes the norm. This function, the colors boundary norm, is used to generate a color map index based on discrete intervals, which is the levels over here. These levels actually define the boundaries of each color scale. And since we want to extend at both the minimum and the maximum end of this color scale, so the number of colors we need is actually the number of levels plus 1. And then we call the subplot function twice for both variable. And we apply the same norm to both subplots, which will let them share the same color scale. And finally, we draw the color bar. The first argument is returned by subplot function, since they share the same color bar, so we can use either of them. And this argument tells Cartopy that this color bar is for both axes. Let's see what we get. Yes, we have this two subplots that share the same color bar. And you can always change the parameter to say the impacts on the figure. For example, we can change the this W space like to 0.1. The distance between the subplots will become bigger. Well, in this example, the size of each subplot is exactly the same, but sometimes we may want the subplots have different size. And this grid spec can help us achieve that. It can customize subplots layouts. Here is an example. We first run the code. We have a map on the left side showing the changes in the annual mean white bubble temperature. We have another plot on the right showing the zonal average curve. And we want this map to be much wider than this line plot. Let's look at how we achieve that. First, we define a function called map to plot the map, and there is nothing special over here. Maybe the only thing new here is that we're passing this alpha equals 0 to this plotting grid line function. This will make the grid line transparent to us, so we'll not see the grid lines, but we'll still plot the labels. We can also set the label size. And then we define another function to plot a zonal average curve. You can see that over here, we use the set ticks position and set label position to make the ticks and labels of y-axis on the right side. And then we define the third function called plot2 to make the whole figure. We define the figure and the figure size. And here we use this grid spec function to create a frame, including 2 columns and 1 rows. And we set the width ratio at 10 and 1. This is to say the first column is 10 times wider than the second column. We can also set the white space. Here, notice that we can actually pass in a negative value over here. Then we add 2 subplots. Notice that rather than passing 1 to 1 and 1 to 2, we pass in spec 0 and spec 1. This is returned by this grid spec function. And then we make the annotation. We choose a color map and define the norm. And then we call this map function to plot the map. We plot the color bar. And then we make the line plot for the zonal average curve. And that's how we get that. Well, let's move on. Sometimes we may want to overlay something on the map, for example, to show the statistical significance. And in this case, we can use a Control F plot with hatches to achieve it. Now let's see this example. We first create a figure and add the axis. We draw the coastlines and we define the levels, the color map, and also the norm. Then we make the plot. If we stop over here, we would get exactly the same map like this one. But now we want to overlay something on this map to show whether the change is statistically significant or not. But because we have only 2 years, the first and last year of this century, so there is no way for us to make a real statistical test. So here we artificially define a p-value array. We set the p-value to be 0.01 if the difference is larger than 5 degrees. Otherwise, we set the p-value to be 0.09. And then we make this plot, make this Control F plot for the p-value. And we make this plot on the same axis. We set a level to be 0, 0.05, and 1. So this 0.01 will fall into this range and will be treated as statistically significant. And the hatches we set as dot and none. So for the first range, it will be dot hatches. And we don't want X-ray to plot color bar. Here we set alpha at 0. This will make the field control plot transparent to us. So we can only see the hatches over here. Well, let's try this. Yes, we can see that we have a plot with some dot hatches to show the statistical significance. If we change this alpha from 0 to 1, let's see. This control plot will be filled with color and we wouldn't be able to see these hatches. Well, in addition, you can also change the density of these dot hatches just by changing the number of the dots over here. Let's say we decrease the number of dots. Yes, the dot hatches is becoming less dense. And we can also change the type of hatches. Right. Now let's get back to the original pattern. You will find that there is a vertical line at the center of this map that the dot hatchet is missing. That's because our longitude varies between 0 and 360, and the plotting function doesn't know that 0 degrees and the 360 degrees is actually the same thing. So there is a discontinuities over here. And this can be addressed by this add cyclic point function over here. We can add a cyclic point over the longitude coordinate. Now let's uncomment the code. We add a cyclic point for both the p-value and the landmask, and we use this new landmask. Yes, problem solved. Well, after all this, let's try to make our final plot. You have actually seen all the things over here. There's nothing new. We first define a map function to plot the map, and we define a line plot function to plot zonal average, and then we define another function called plot3 to make the whole figure. We use this grid spec to customize the size of each subplot. And then we call the map function and the line plot function to make each individual subplot. Let's try that. But before we actually call this plotting function, I want to mention that we can use this matplotlib savefig function to save our figure. Here, I save this figure as a PDF, which is a vector format. And I shouldn't set it as DPI because it's a vector format. So I delete that. And this bbox inches equal height is trying to remove all the extra white space that around our figure. So now let's try to make this plot. Well, this is our final plot, and let's see if it has successfully output this as a PDF. Yeah, we can see there's a PDF over here called the final plot. Let's open that. Well, that's our final plot. It looks great. Okay, this is the end of this video. Thanks for watching. See you next time.